I guess we can start now. It's around time. So welcome to CPP's third session. We will start with Wojciech Nawrocki and talking about a certifying proof assistant for synthetic mathematics in Lean.
Okay, thank you. Is the mic? Yeah. So I'm Wojciech. This is joint work with a few people, including Mario Carneiro, who's over there, so you can ask him questions as well. The aim of this work is to make a certain kind of mathematical proof using synthetic reasoning, which I will explain what that is, formalizable. That is to say, we sort of are claiming that these proofs exist in the informal literature, but it's between difficult to impossible to formalize them right now without doing something that maybe resembles what we are doing here. So what is synthetic mathematics about? This is defined via a dichotomy between two approaches. One is synthetic, the other is called analytic. In synthetic math, what you do is you take an area of mathematical inquiry and you axiomatize it in terms of some kind of primitives that don't have any further like internal structure. Whereas in an analytic approach, you would break things apart. So let me give you an example of what that means. So this terminology came from geometry. And the classic geometry textbook is Euclid's Elements from 2,000 years ago or so. And the first proposition says that if you have a finite line segment between 2 points P and Q, like here, then you can construct an equilateral triangle on that line segment. And the way that works is you draw a circle around P that goes through Q. Then you draw another circle around Q that goes through P. And then you observe that these circles intersect. So you can pick one of the points of intersection as R, and that would be the third vertex of our triangle. And you can prove that this triangle is equilateral. And the thing about this proof is that it never mentions any coordinates. So these are points and lines, but it's not like we are measuring numerically the slope or the position of any of these things. They're just kind of irreducible objects. And this is in contrast to Descartes' Cartesian approach to geometry, where points are in fact elements of the Cartesian plane, so pairs of real numbers. And the way that you would construct R in this approach is you just do some like vector algebra. And so that's the dichotomy, and the relation between them is just that the Euclidean geometry you could realize as a, let's say, first order theory, and then the Cartesian plane is a model of that. So modern synthetic mathematics tends to use dependent types on the side of the theories and categories with extra structure on the side of models. So an example of that is homotopy type theory, which axiomatizes classical homotopy theory. And in this setup, one class of models that we might care about interprets types, the synthetic types, as analytically as groupoids. That is to say, categories where all the morphisms are isomorphisms. So for example, we can write down like the type of Booleans in the theory, and semantically that is going to be two disconnected objects. But also in homotopy type theory, we can do other constructions like higher inductive types. So this circle type has a single constructor for the point, and then a loop generator. And it turns out that that is isomorphic as a group to integers with addition. And then the thing we want to say now is that the stuff on the left-hand side, like the types in homotopy type theory, it is possible to formalize in many languages and frameworks like cubical Agda or Unimath or one of those things. The stuff on the right you can also do because, for instance, Lean's MathLib library of mathematics has a definition of what a groupoid is. But there isn't really some kind of tool that would allow you to speak about both of those things at the same time and kind of interchangeably. And you might want to do that because there are some proofs in the literature, like this example. So you're not supposed to understand the math, it's just the colors are relevant. So this is a random corollary from Ingo Blechschmidt's thesis on synthetic algebraic geometry. And the thing to notice here is that kind of it freely mixes the theory reasoning, which is in orange, with the model reasoning, which is in blue. So the blue stuff is like classical algebraic geometry, and the orange stuff is type theory and constructive ring theory and so forth. So the goal of this project is to formally verify these kinds of theory model connections in a single system, and we chose Lean for that. So the concrete things we did is first we defined a deep embedding of Martin-Löf type theories with universes, pi types, sigma types, identity types as well as base constants. And using this language, you can write down homotopy type theory, although we don't have inductive types. Then on the side of the semantics, we defined natural model semantics, which are related, or actually almost the same as categories with families, if you know what those are. And we proved that those are sound for the syntax, so anything you prove in the theory actually means something semantically. And then we constructed this proof assistant called Syntlean that allows you to work with points 1 and 2 exchangeably or interchangeably. So before going on into details of all these 3 things, let me just give you an example of how you might use Syntlean. So this is lean code. You could try this in our repository. We define this command called declare theory, which you would use as the starting point to declare some theory. And then in that theory, we can state what the axioms of it are. I called this one point TT because it's just the theory of a single type with a single point in it. So we have an axiomatic type X and an axiomatic point P in X. And then from the perspective of the theory, you can print out what that is. Well, it's just an axiom. It's P has type X. But also, you can print it from like the meta-level perspective of lean. And from that perspective, it's a structure of type checked axiom, which includes a deep embedding of the type of P, as well as a proof in the field WFTP that proves in lean that this type is well formed according to the rules of Martin-Löf type theory. And then on the side of the semantics, you can define something that is called the natural model universe, and this serves as a model for the theory. Let's say that we have some semantic objects mx and mp that are supposed to model x and p. And because these are categorical semantics, those things are arrows in some kind of category. And then we can connect the syntax to the semantics with an interpretation function that takes the syntactic x to the semantic x and so on. And, having done that, if we make more constructions in the theory, like we define a point q, which is definitionally equal to p, then the interpretation of q is just p. So it's what you would expect. Of course, you can do much more complicated things than this. That's just an example. OK, so having said what the usage is, I will just go through the 3 components. That is the syntax, the semantics, and the proof assistant. The syntax is very standard Martin-Löf type theory. There's nothing surprising here. One thing that is maybe unusual is that it's stratified by the universe levels. So every judgment is parameterized by which universe level it's at. This is sometimes called universes à la Cocon. And we have a finite hierarchy of universe levels. So there are only type universes up to some finite level L max. The reason for that is like Gödelian restrictions. We could not have countably many of these. And then, if we have an element of a universe, then EL of that is a type, and so forth. We have pi types, which one thing relevant about these is that the universe level of a pi type is the maximum of the 2 universe levels. The reason for this is that that's what lean does. And we want our deep embedding of type theory to match lean's rules closely, because this will allow us to reuse a lot of the lean infrastructure for elaborating tactics and so on to work in this type theory. And the final thing to notice is that all of these judgments are parameterized by this bold T. So that is the theory. And the rule for it is just that, well, if you have a constant of some type in the theory, then you can use it in the embedding. So like previously we had a point P of type X, you could do that. In lean, it's a mutually inductive family of proof irrelevant propositions over raw syntax. We have some basic syntactic meta theory. This is very standard and it's been done many times before. We know that substitution is admissible for the system. We know that it has various inversion principles, like if A and B are definitionally equal types, then A must have been a type to begin with, and same for B. We have an axiom that pi types are injective. This is necessary for the type checker. This has also been proven many times, including in various proof assistants, for systems that look very similar to this one. The reason we didn't do it is that it's not an easy proof, and it's not really the focus of this work, so we focused on the other aspects. But in principle, I believe this should be provable for the system. OK, then the semantics, we use categorical semantics. So a natural model universe is something that lives in a pre-sheaf category over the category of contexts denoted by CTX here. And what that is a natural transformation between two pre-sheaves, the pre-sheaf of terms and the pre-sheaf of types. And then if in the syntax we have a type A and a context extended by A, as well as a term T, then you interpret those things in the semantics as follows. The context gets interpreted as an object of CTX, and that becomes a pre-sheaf using the Yoneda embedding. Then the type is interpreted as an arrow into the pre-sheaf of types. The extended context is interpreted as another element of CTX, and the condition from this orange arrow to make it a universe is that pullbacks of representable pre-sheafs have to be representable as well. So that's how we interpret the extended context, and then terms become arrows like this. In Lean, it's probably what you would expect. We have two pre-sheaves, a map between them, and some function that gives us a choice of this corner for every arrow down here. We have to show that this semantics is sound for the syntax. This also is a very standard proof that goes back to 90s work by Thomas Streiche. The way that that works is that you define partial maps on syntax into the semantics. So for instance, for every context, which is syntactically just a list of types, we get an object on the category, but this map is partial because not every context makes sense. And then after defining all these partial maps, we prove that the soundness holds, which is to say that, for instance, on a well-defined type, the interpretation of that type is defined, and for definitionally equal types, the semantics are equal as well. This was previously done, for instance, by De Boer and co-authors in ACTA. Okay, so if you've fallen asleep at the category theory part, now there's no more category theory. It will be a proof assistant implementation section. So the way the proof assistant works is it's certificate producing. So what that means is that if you write down an axiom like this, so from the example, then it produces this structure, just an ordinary Lean structure with the deep embedding and this proof that TP is well formed. So the pipeline for constructing that is as follows. We begin with the so-called vernacular, so that's what the user actually types into the proof assistant. That gets sent to the Lean elaborator, and this is kind of the crucial part that makes this somewhat easy to implement. Because the deep embedding and the type theory that we defined is very close to Lean's, we can just reuse Lean elaboration. And this produces an internal representation of, in this case, the axiom, which might include the name and some representation of the type. Then we translate it into our language, so the synth-Lean type theory. But the translation is very simple. It's almost the identity map. There's some annotations we have to insert and so on, but there is nothing complicated going on there. And then once that type is produced, we type check it, and the type checker produces a certificate, that is to say just a Lean proof term, that certifies that the type TP is well typed. And that gets sent back to the, again, Lean kernel, so that Lean can certify or like check that nothing went wrong. And yeah, the white parts are just Lean components. The colored parts are what we implemented. The proof assistant and the type checker in particular is certificate producing, meaning it's a tactic, and it's a partial, it's built out of a bunch of partial functions. So it uses normalization by evaluation. So here's an example of one function that makes up the type checker, and this function evaluates a type. So it evaluates a type T in the environment n of NB values. And like I said, it lives in the Lean tactic monad, which is called meta M. And it produces a VT value, as well as a certificate that this value is, well, satisfies its post condition. And the post condition is that if T was well formed to begin with, and the environment is related to some substitution sigma, then the output Vt is related to the substituting sigma into T. So this related relation with the squiggly equals is a fairly simple inductive invariant. In particular, we don't need to do logical relations or anything like that, because we don't need to prove that this thing normalizes or terminates. So yeah, no termination encoding, like the Bove-Capretta method is needed for this. We have some somewhat standard optimizations that are done these days in NB implementations, like weakening of terms is free because it uses the Brown levels. Lambdas are represented as defunctionalized closures, like in the work of Andreas Abel. And in those certificates, we also share subterms using hash consing to minimize their size somewhat. A few other aspects of the formalization. We needed to do a lot of dependent rewriting. So we implemented a tactic for that, RW-bang, jointly with Aaron Liu. And now that's in Mathlib and seems to be used for other things that are not our project. In category theory, there are a lot of naturality laws that are obvious in the sense that you probably not even mention them on paper. But encoding them in a formal system tends to cause some issues. And we've found we've experimented with various ways of doing that. And unfortunately, the most concise ones are the slowest. But maybe there is some hope for improving that. So there's a link to a discussion here. We work with these deeply embedded judgmental equalities, and Lean does not have quotient inductive types. That is to say, we can't just quotient the syntax by the definitional equalities, which leads to so-called setoid hell. But also, I'm told that if you do have quotient inductive types, you're just in a different kind of hell. So nobody seems to really know how to work with this efficiently. As far as I know, this construction of certificates for normalization is new. But there is some similarities to this project by Esther Kolmatskaya that's on GitHub and does this for simply typed lambda calculus. We rely quite heavily on polynomial functors, and there is a library that's being co-developed for that called Poly. And the final thing I wanted to mention is this is all part of a larger project called HotLean, whose aim is to do homotopy type theory in Lean, but with the difference to previous approaches being that we don't add any axioms really, and it's not a foundational change. Instead, everything is supposed to compile down in the sense that I just described to some kind of model that you might care about, like groupoids or simplicial sets or something like that. Yeah, so that's all I have. Thank you.
And there is time for some questions.
Hi, thanks for the talk. It's really cool. So I was wondering, so there's a kind of a similar project in spirit is what's happening in Iris in Rock, where you also kind of work with like kind of a layer, kind of a proof assistant embedded in another proof assistant. And there one big issue is that you have to recode all of the tactics and all of the basic things of the proof assistant in your embedded one. And here, can you avoid, like, to what extent can you avoid that by using this thing that you, like, use the elaboration of Lean itself to, like, do most of the work? Like, do you still need to, give to the users, again, a bunch of new tactics that are going to be kind of the same further level of your proof assistant as the ones at the level of the Lean proof assistant? Does that make sense?
Yeah, I think so. So no, because we are reusing the Lean elaborator, you can in principle use all the ordinary Lean tactics from Mathlib and so forth. There is a big caveat there, which is that most synthetic theories are constructive, and Lean tactics tend to use classical axioms a lot. But modulo that, you can just use them without writing new ones. Does that?
I saw, maybe this is a bit of a technical question, but how do you handle top-level scope in your theories? Because I saw that like when you have this stuff, it's just like a symbol Q, or like a symbol X, a symbol P. Is that like, do you have any sort of notion of scope in .tt that would like allow you to have different modules with, I don't know, yeah.
Oh, okay. Maybe we can also talk later because I'm not entirely sure what you mean by scope. But to answer like a hypothetical understanding of your question, Lean has namespaces for organizing definitions, and you can similarly put these things in namespaces. Does that help?
Let's talk about this.
Yeah.
talk. I was wondering, in Martin-Love type theory, if you have extensional Martin-Love type theory, the semantics in the categorical semantics becomes easier sometimes, at least in display map categories. Can you elaborate a bit on this, if it's on the difference between intensional and extensional, or if you're trying to support it?
So people use extensional in different ways. Do you mean equality reflection, or okay? So yeah, so the language, the deep embedding we use does not have equality reflection. It's intentional, like lean. Yeah, and the semantics is intentional as well. So indeed, we have to do various, for instance, in the extensional semantics, identity types are more or less just a simple, described simply as a pullback. In this setting, they're not. You have to do a bunch of constructions. We do them. Does that?
I just wanted to add to that we do have both kinds of equality. There's like EQ and ID, and one of them was an intentional. It satisfied an intentional rule, and then the other one had an equality reflection rule. And because HOT supports having those both, they're just not the same type.
There's time for one more quick question, if there is one. Otherwise, we can.
Have you what kind of thing can you add to your theory? So you can add axioms, but can you add new conversion rule on this axiom? Or?
No, so we have not experimented with that. I mean, the reason is, in general, it becomes undecidable. Of course, there are many works recently, like adding those to Agda, and I think Rock as well. We haven't tried it, to answer it simply. It would be an interesting thing to try.
Okay, we should switch speaker now. But let's thank Wojciech first.